CLI a cross-platform IDE for C and C++. Download now.
I'm really honored to be giving the closing keynote at this conference. This is the first time I'm giving a keynote. I've been I asked on tips on how to give a keynote. Some people said they really like technical keynotes. Some people said they really don't like technical keynotes. So I've just decided to just do my own thing and give the talk as I would usually do it, and hope that's okay with you. So I'm going to talk about functional programming in C++. So first of all, the question obviously is, what does this work? No, there we go. What is functional programming? Now, functional programming is best contrasted with imperative programming. So imperative programming is a programming style where you specify instructions that manipulate some states in order to achieve a goal. And C and C++ are mostly imperative programming languages. So you've got statements that manipulate various variables, and then you do your program. And also the CPU itself is imperative. Like you've got assembly instructions that modify memory, set registers to new value, and that's how you do stuff. But for a non-technical example, for example, an IKEA menu is also an example of an imperative programming thing. You've got the sequences of steps that you need to do in order to assemble your furniture. This is in sharp contrast to declarative programming. So in declarative programming, you only specify the outcome. Like what is it that you want to do? And then the system figures out how to achieve it. And Haskell is a declarative programming language, more about it on the next slide, but also Prolog. Prolog is a declarative language where you essentially specify a bunch of facts, and then you can ask your system to whether some other condition is true, and it will infer that based from the facts. Something you might be familiar with is a formal grammar. So formal grammar is also a form of declarative programming. You specify sort of syntax rules in order to describe what is valid. And then there's some parser that will figure out based on those rules how to parse that grammar. Or the thermostat in this room, I've set it to the desired target temperature, and then the system will figure out how to what to do in order to achieve that temperature. And functional programming is a form of declarative programming where you mostly compose functions. So this is a bit of Haskell code. This is a Haskell definition of the faculty function. So the faculty function takes an integer and returns an integer, and then we specify rules. So we say that the faculty of 0 is 1, and the faculty of n is n times the faculty of n minus 1. And there is no temporal ordering between those two rules. Like in C++ code, you would have a bunch of statements, one after the other, and then they're executed in that order. This isn't the case here. You can put those in any order you want. For a more complex example, there's a sort. So a sort takes a list of integers and returns a list of integer. And then we also specify rules. So we say that the sort of the empty list is the empty list, and the sort of a non-empty list that starts with the member x, and then we've got the x's as our tail, is given by taking all the elements on the left of x, then x, and all the elements on the right of x, putting them together, and then our list is sorted, where we say that the elements on the left are all those that are less than x, and the elements on the right are all those that are greater than or equal to x. And this is some sort of a non-in-place quicksort implementation of sort, if you want. And this is a very declarative way. You only specify what you want. You just define what sort it is, and you don't specify how it's evaluated. This is for the Haskell compiler to figure. Now, why should you use functional programming? Functional programming is really nice because it eliminates state. And state is really annoying because state, like mutable state, where you store some values, that's where all the bugs is, right? You've got what if the state is invalid? What if it is some invariance? So you've got multiple variables, and one always has to be a multiple of the other or something. And while updating them, you've broken the invariant, and you've got a bug because of that. And it's just messy to deal with. And if you don't have state, you don't have any bugs due to invalid states. Or what if you're having a complex class hierarchy with a bunch of shared pointer that point to other shared pointer, and then you've got the weird object graph, and then you try to remove this element, and then everything falls apart because you've got too many references to it and stuff like that. If you don't have any of the sort of intertwined object references because you don't have state, you don't have any bugs there either. And because you don't have any state, you don't have any race conditions because nothing modifies any shared state, which makes it really trivial to parallelize. Because if you don't share anything, you can just execute stuff in parallel. So if functional programming is so great, why isn't this a functional programming conferences, right? Like, why don't we use it everywhere? Well, we don't use it anywhere because fundamentally functional programming does not map neatly to hardware. The CPU is not functional. The CPU is imperative. It executes instructions. So every time we sort of use functional programming, there's a bit of a penalty, right? It makes it harder to optimize because the functional programming concepts don't directly map to the hardware instructions. Also makes it harder to use native tools like a native debugger or native profiler that talk about assembly instructions and CPU registers, because the code you write is so far removed from that, it's a bit awkward to use. And if you want to interact with the outside world, with like native libraries or the OS APIs, it's a bit awkward, right? Because again, you don't neatly map to the expected concept, and like most of the world is imperative. So if you go from a purely functional approach, it's a bit annoying to use. So as with everything in software engineering, whether you use functional programming or a particular function programming language is a trade-off, right? It has its advantages, it has its disadvantages, and it's well suited for some problems and really bad for others. Luckily, we're using C++, and C++ isn't a pure functional programming language. That means that we don't need to use functional programming for everything. We can pick and choose when to use functional programming and when to use more imperative stuff. And crucially, fundamentally, functional programming is all about the composition. Like the definition of functional programming was declarative programming by composing functions. And composition is really all about. And that means that in C++, we can write building blocks using efficient, optimized, and well-tested, hopefully, C++ code, and then we compose them using functional programming paradigms. And that way, we sort of get the best of both worlds. So in the keynote, I'm going to look at three things: how to compose algorithms, how to compose functions in general, and finally, how to compose I/O. So let's start with composing algorithms. I've collected a couple of like lead code style problems and show you how they can be solved using a functional programming mindset. So this is a really simple problem. Our input is a non-empty list of integers, and the output is, well, the biggest magnitude of an odd integer in the list. So what this means, if this is our integers, then the output is 7, because 7 is the biggest, the odd number with the biggest magnitude, right? We've got -7, magnitude is 7, so that is the biggest magnitude. And it's straightforward to write using imperative programming, right? So this is our function. It takes an arbitrary range using a forwarding reference, because for technical reasons, this is how you have to pass ranges in C++ nowadays. And then we simply loop over all of them, compute the magnitude using the absolute value function, check if it's odd, and if so, then we update our candidate, which is initially -1. So that ensures that the first time we go around, right, we update it, and then in the end, we return the candidate, right? This is an imperative program. We specify a sequence of instructions on how to solve it. Well, how can we do it in more functional? Well, functional programming is about composition. So the question you always need to ask yourself is, what is the composition? And here there are three subproblems. The first subproblem is we want to compute the magnitude of each number. And the second problem, we want to filter out the even numbers and keep only the odd ones, and then we'll find the maximum. And now the approach is to like write the building blocks and then compose them. And luckily, we don't need to write the building blocks because the standard library provides them for us. So for example, computing the magnitude of each number can be done by using the transform algorithm. The transform algorithm takes a range and simply adds it to the vector of magnitudes here, using the back inserter, and the transformation function returns the absolute value. Now we've got all the magnitudes. We want to filter out the even numbers, and for that we use copyif and copy all the values over to a new container. And finally, we can use the max algorithm to find the maximum. That way we reused like fundamental building blocks and composed them. As an aside, this stdr simply means that we use the stood ranges algorithm. So before, you would need to write like since C++98, you've got the algorithms that takes iterator pairs, and since C++20, you can use range algorithms. You can simply pass in the container directly and don't have to worry with the begin method. And for the slide, I will just use the stdr to indicate that I'm doing that. Now, while this approach works, it's not really great, because fundamentally it uses eager composition. This means that we have to create intermediate containers. We eagerly compute all the results, even if we don't necessarily need them, right? Because each step we compute everything. And we haven't really eliminated any state. We still have these intermediate states that we use in our building. So can we do better? And yes, we can using views, because views is something that allows us to do lazy composition. So view is simply a lazy range whose values are computed on demand. So it's more like a description on how to do something. It doesn't actually do anything yet. So when you take views or when you compose views, you don't actually do anything. And the actual work only starts when you start iterating. And this allows you to do like a sort of functional pipeline and eliminates the state. So this is how it would look with views. And again, then defined in namespace std views, so I use the stdv for the slides. So to compute the magnitude of each number, we use the transform view. Now the transform view takes our range as input via the pipe, and then it simply applies the absolute value to each element. But crucially, this is lazy. So this line doesn't actually do anything. It merely describes the action that we want to do. It takes the range and transforms each element using the absolute value function when we start iterating. So this doesn't do anything. And then we use the filter view to filter out the even numbers. This takes the predicate again, and we filter them out, and we take the magnitudes as our input. And this also doesn't do anything because we merely composed views. So now we've got a pipeline that when you start iterating over them, you will get the absolute value of the odd numbers. And we do that by passing it to the maximum algorithm as before. So we pass our pipeline to the maximum algorithm. This is the eager thing that's doing actual work. This is where we start iterating. This is where we do the computation. And so you might say, oh, these variables, they are still state, but they aren't. They're simply labels to the intermediate steps in the pipelines. So usually you would write them inline and just have one pipeline that you pass to max. And this is very compact, very declarative way of solving the problems, where we don't have to deal with any state because we don't have any state. This is really nice. So the general composition shape we've seen here is that of a composition shape that takes a range and returns a range, but with potentially different values or different size. So we see in transform applies a function to each element, and usually this is called map, but not in C++. In C++ it's called transform. Then we've got filter. Filter keeps only the elements that satisfy a predicate. And similarly, there are views like take while or drop while that like remove a prefix or suffix from our range. And then we see in the composition shape that takes a range and returns some derived value. For example, the maximum or the minimum element using the algorithm. And this eagerly computes something by iterating over the range. Similarly, there's count, which counts the elements that satisfy some predicates. All of, any of, and none of, which do what they say. Find or search, which like finds or searches iterators or subviews of a subrange satisfying some condition. And all of these take a range and produces a derived value by actually doing some work. For another example, let's consider this problem. So we've got two lists of integers as the input and a number target. And as output, we want two integers, one from each list, whose sum is target. So if these are our lists and the target is 12, then the output would be 4 and 8, because 4 is from this list, 8 is from that list, and together they sum to 12. This is how you would do it imperatively. You have two loops. You loop over all elements in range 1 and all elements in range 2. If there's sum to target, then you return that. Otherwise, return nothing. How to do it functionally? Well, you have to ask again, what is the composition? In this case, we have two things. First, we generate all the pairs, and then we find the appropriate pair. So to generate all the pairs, we can use the Cartesian product view. And the Cartesian product view corresponds to the nested loops. So it's all pairs where one element ranges from range 1 and one element ranges from range 2. So every time you have like two nested loops or more nested loops, you can use Cartesian product. And then we want to find the pair using the sum target. And for that, we use findif. This is an algorithm. So this is the one that's actually doing any work. The first line doesn't do anything. It doesn't allocate anything. It doesn't generate a vector of pairs or anything. It simply describes how to iterate. And then the findif algorithm will iterate over it. And again, this doesn't do anything. This doesn't do any allocation either. It simply uses iterators in a very clever way to iterate over them. And then the predicate takes our pair, and we want to see whether the sum of the pair maps the target. And if so, then we found it, return the iterator, and return it here at the end. Like it's a bit awkward. You want to get an option out of there, so you have to do this. Now you might ask yourself, okay, this is all nice, but like the code with the two nested loops, that was also nice. That was like nicely expressible. What's the advantage? Well, the advantage here is that because we've given it in a very declarative way, very abstracted away the things and simply described what we wanted to do, we can very easily change how we're doing it. For example, this first, so This code is kind of ugly, right? Like you have to do the unpacking of the tuple, and then you have to turn that into an optional. So at Thinkcell, we really like to write this kind of code, but like not as ugly. So we've got our find if, which takes like a thing where we specify what the return value is. So we say in this case we want to return the value or none, right? And this will automatically return an optional of the value type. And then also in the predicates, we can, like, instead of taking a tuple, we can directly take the two elements and return the target. And this will like automatically unpack it and just makes it a bit nicer. But anyways, so what's the advantage of using it in a functional programming way? Well, we can very easily, for example, parallelize the entire thing. So just by changing the find if algorithm from find if to one that takes this par unseek, it means, hey, please go ahead and execute that in parallel. Because the algorithm knows how to parallelize itself, and all we're doing is invoking an algorithm, and now we've got code that runs in parallel. This requires C++26. It was just voted in at the last meeting. But the new thing is only that the std ranges algorithms are parallelized. Otherwise, it's available since C++17, but you have to pass the iterator pair. And now, by just changing this line, it runs in parallel. And this is possible because functional programming doesn't have any state, so it's very easy to parallelize. Another thing, just for completeness, this algorithm fundamentally is like still quadratic because we like iterate over quadratically many things. So just for reference, this is like a more efficient way where we use a lookup table. So we iterate only over like one range at a time and check our lookup table, which contains a set of all the elements from range 1. So by using 2, we can turn an arbitrary range into a container. In this case, the container is an unknown.set. And then we have a very efficient lookup. So as we iterate over elements, we want to see whether we have a corresponding one in the lookup table. And this makes it only linear. And in the end, we can know that we found a tuple. Right? And again, this is not a pure functional programming style, but that's okay because we're in C++. We don't need to do it. We've got a bit of state that we've created here. But since we don't mutate it, it's not really a big problem. The general composition shape is here. We've got multiple ranges, and we want to return a single range. And what we can do, for example, is Cartesian product. This produces a tuple of all possible element combinations, and there are n times n many of those. Then we've got zip. Zip is a tuple of corresponding elements. So it iterates over them in lockstep, and then you get a tuple of each element from the zip. So the smaller of n or m many elements, this is surprisingly useful, especially also like a zip with the range with itself slightly shifted, and then you get like adjacent pairs and stuff like that. And in C++26, we're going to get concat, and this is simply all elements of the range, one after the other. So n plus n elements. So first all from the first range, then all from the second range, and so on. For another problem, this is actually like a non-trivial problem, I'd say. So let's consider the input is a list of integers, and the output is the length of the longest contiguous subsequence of increasing numbers. And again, the example should make that clear. So here's the input, list of integers, and in this case, the output would be 4, because the longest contiguous subsequence of increasing numbers is 2, 4, 5, 7, right, which is length 4. So this is how the code would look in imperative programming way. Essentially, what we're doing is we're iterating over it and checking whether the current element can still be part of our current subsequence. If so, we increase the length of the current subsequence, and otherwise we need to start a new subsequence by like updating the current maximum and resetting the length. And then we have to like wrangle some state like the previous one, and that's correctly initialize the stuff to make sure that the comparisons all work out. And then in the end, don't forget, what if the last subsequence is the one that actually ends? So current length could still be bigger than max length, simply if we like reach the end without ending the subsequence. So you have to return the maximum. And this is the point where it's like a non-trivial amount of stuff in your head, if you want to understand that. So how we can do it using composition? What are the building blocks? Well, we want to split the list into each chunk of increasing numbers. Then we determine the size of each chunk and return the maximum. And that is the longest subsequence of increasing number. And it's a nice one-liner. So we start with our range, and then we use the chunk by view. Now the chunk by view takes a binary predicate and sort of splits the range into chunks at the borders where the predicate changes value. So it invokes 2 adjacent elements, passes them to the predicate, and when the predicate returns false, then it splits them into chunks. So it would first invoke less with like 1 and 3, since 1 is less then 3, we add 3 to the current chunk. Then we invoke it with 3 and 2. But since 3 is no longer less than 2, we split the chunk and start a new chunk with 2. And then we keep adding stuff to this. And then we split again. And then we end off with our chunks. And again, this happens completely lazily. It doesn't do any allocation. It only happens as we reach it, as we iterate over it. Finally, we've got now a list of chunks. And we want to get the size of each one. So we pipe them into transform, ask for the size. And then we've got the list of sizes of the chunks. And then we simply want the maximum. And that's how you get the longest increasing list of subsequence numbers by intelligently composing them out of smaller building blocks in a very declarative. So the composition shape here is we have a range and we want to get a range of ranges. So for example, we've got chunk by. This splits the range into chunks where borders don't satisfy a binary predicate. Then we've got split. This splits the range at a separator, so you can take a range of like characters and split them as spaces, and then you've got a range of words. And then we also got slide. This is simply a range of sliding windows. And there's a question whether I want to use std size on this slide. So here I'm using std size to get the size of each chunk. Alternatively, there's also a function distance, which gives the distance between the begin and the end of the chunk. This is essentially the same thing for a range, except the size is like unsigned and the distance is a signed value. I personally would never call distance on ranges. I would only call distance when I've got 2 iterators, because I find it more naturally to ask what is the distance between that iterator and that iterator, as opposed to like what is the distance of a range. Finally, this problem is a somewhat common interview question, I think. So the input is a string and the output is a string where all the words, where word is a sequence of letters, are reversed. So if our input is hello world, this is the output. We've simply reversed each word, but left otherwise the order of words the same. And the imperative code starts to get really ugly. Like we iterate over the characters using iterators, and if we add the boundary of a word, which is that like, so the current one is a letter, but the previous one isn't, remember to correctly initialize it to handle the boundary case. Then we go ahead and find the end of the word and reverse it in place. So we have mutating state in here. As we iterate our string, we like change it. So in the middle of the loop, it's like partially changed and so on. This is always a bit annoying because what if, I don't know, an exception is thrown and the change is observed or something like that. Otherwise, we need to skip over the word if it's not a word. Then we need to keep track of the previous one. So this requires like a bidirectional iterator. So it's not as generic as it could be. And then return the string. Right? And this is starting to get like really messy. It's really nice if we think about the composition again. So what is the composition? We first split the string into words. Then we reverse each chunk that is a word. And then we put all the chunks back together. And this is how we can do it. So we start with our string. And again, we use chunk by to split it into words, because we can detect a word where like one character is alphanumeric and the other one isn't. That means we add the boundary of a word. And this correctly handles the case of where you've got like multiple non-word characters in between words, right? They would all be grouped together into one chunk. So chunk by, this is our boundary condition. It splits it every time this predicate changes value. Then we've got a list of words and also non-words. And so we want to transform each chunk. So transform gets called on the actual chunks again. And if it's like a word, we know it's a word when like the first character is alphanumeric, then we reverse it. Otherwise, we leave it unchanged. And the result of this is a list of like words like of the chunks that are already like correctly reversed. It's just a range of ranges, and we want a single range. So we use join. And join simply takes a range of ranges and turns it into range by adding like all the elements one after the other. And up until this point, we haven't actually done anything. We've just declaratively built a pipeline, because all of those are completely lazy views that work without any allocation, without doing anything. And only when we call std_ranges2 do we actually start doing it. Because std_ranges2 is an algorithm. It starts iterating over a pipeline, and as it receives characters, it turns them into a std string. And then we've got the resulting string. Now, one slight caveat, this doesn't compile yet, because the return type of this predicate, at one point we return like reverse of a chunk and otherwise the chunk. And because this is a view, it doesn't modify the chunk in place. This happens lazily. And it's like a reverse view, and this is just a chunk. So it's like different return types. So it doesn't compile. One way to fix it is to go ahead and say, okay, eagerly turn those into a string. Now both branches return a stud string and we're good. But we just do eager allocation and start reversing stuff and so on. And that's not really nice. So I think we have a really common utility for that, conditional range. Conditional range sort of pushes the branch into the view itself. So this returns a single view that either iterates over this branch or over this one, but crucially, we don't have to worry about the type. So internally, it has iterators that are like variants. It's either this iterator of this branch or the iterator of that branch, and then it increments the property. And in this case, because reverse could actually be implemented to use the same iterator, then it would just initialize the appropriate values and make it really efficient. I plan on proposing that for C++29 because it's a really useful utility. But with that, we've reversed over it. And I want to highlight that what we're doing here is we're taking a single range, we're splitting it into a range of ranges, we're transforming this range of range, and then we're joining it back together. And this turns a range of ranges back into a range. And this is going to become really common later. So the composition shape is here the one of join, right? So we take a range of ranges and we return a single range. And you can use join, it simply flattens it back together. Or to join with flatten it, but inserts a separator between them. And that's how you, for example, turn a list of integers into a string where the integers are separated by commas. You transform each integer into a string, and then you join them with a comma. Now, all of those problems were sort of nicely suited towards range algorithms because they were talking about ranges. They were talking about lists of numbers and things. So obviously, range algorithm makes sense. So this is an example where we don't have a range. Instead, our input is just a number. And what we want is the smallest Fibonacci number that is greater than that. So for example, if the input is 9, then the output would be 13. Because the 6th Fibonacci number is 8 and the 7th Fibonacci number is 13. So 13 is the smallest Fibonacci number greater than. How do we do that? I'm skipping over the imperative code and just directly look at the composition. So what is the composition? Well, on a very high level, the composition is generate all Fibonacci numbers and then find the first one that's greater than X. And if we generate all Fibonacci numbers in ascending order, then we can just stop. Because then by definition, when we found one that's greater, that is the first. So how do we do that? Well, something like this. So this line generates all the Fibonacci numbers somehow, and then we just use findif. Now there are infinitely many Fibonacci numbers. Well, I mean, we are dealing with ints here, so there are only finitely many Fibonacci numbers that fit in an int, and it's not actually that many because they grow really fast. But still, it's we don't want to generate all Fibonacci numbers eagerly. Luckily, we can use views because with views, it's lazy. And as we iterate over all Fibonacci numbers, we will only compute them up to a given point. And as soon as the predicate returns true, we stop generating Fibonacci numbers and have done it lazily only as much as necessary. So this is one somewhat naive way on how to do it, but the pattern is really useful. So I want to highlight it. So we use iota. Iota is a view. So iota is a Greek letter for some reason. But iota is a view that generates increasing integers. So we start with 0 and generates 1, 2, 3, and so on forever. Well, not forever. Eventually, we will have integer overflow, but principle, theoretically. And then we pipe them into transform. And transform takes all of those integers and passes them to the Fibonacci field. So let's suppose we have the function that takes a number and returns the Fibonacci number. And that gives us a list of Fibonacci numbers. And then, again, because this is lazy, this doesn't do anything. Only when we start iterating over it do we actually do stuff. This is a very functional style way of defining the Fibonacci numbers. So n is less than 1, then we return n unchanged. Otherwise, the sum of the two previous ones. And it's also horribly inefficient, right? It's exponential time or something. But luckily, we don't need to do it functionally. We're in C++, so we can just use state. And in this case, the state we need are the two previous ones, and then we just advance it and get the next one. And I use iota again to be fancy in our follow. And this still isn't the most efficient one because you can use the matrix exponentiation trick or something. But let's just stick it with that. The bigger problem that we have is that we invoke fib with each number increasing sequence. And every time we start it back at 0 and recompute all the work that we just did in the previous iteration. So it would be much nicer if we could sort of remember the previous state. And we can do that by using std generator. So std generator allows us to define ranges very easily. So generator is a coroutine that yields values. So in this case, we can just write a function that in an infinite loop yields values. And every time it reaches the co-yield statement, it returns to the caller and pauses execution. And then we can later continue, right at this point, get the next one, and yield it again. And so if we take our generator and pass it to findif, we can use very efficiently generate all the Fibonacci numbers. Because findif will start iterating it. So first of all, this line again is lazy. It doesn't do anything yet. And only findif is the one that's driving the execution. So when findif starts executing, we start executing the generator until the first yield. And this is the result that findif gets first. That is then passed to the predicate. It's still small enough. So we continue from the yield point, do the next one, yield it again, do the next one, yield it again, until we stopped, at which point we stop executing the generator. So the composition shape is here creating a range out of nothing. And a really useful one is using iota to first start with numbers and then use transform to turn them into the actual values. But if that's a bit too wasteful, then you can also use a generator and co-yield, and then you can easily generate an arbitrary range of values. So the takeaway here is when you monocompile algorithms, try to identify small building blocks for solving a problem. To create ranges, use iota and generator. To transform ranges, use transform and filter. To combine multiple ranges into one, use the Cartesian product, zip, or concat view. To split ranges, use split or chunk by. And to join ranges, use join and join with. And that's how you can sort of describe a range in a pipeline. And then once you've got a range with the appropriate pipeline, use algorithms, the various folds like max, min, count, all of, or also searches. And just these tools can get you really far in solving various problems. In a very easy to understand way, because you're just composing individual building blocks. And if you do that, composing algorithms minimizes the use of for. Sean Perrin famously said no while loops, and this is how you get it, by composing algorithms and views. Now let's look at functions more generally. So this is something you might want to do, like unsubscribe a user from the mailing list. To do that, you look up the user, giving its ID, you get its email, and you remove it from the subscription list. In a way, this is a very straightforward composition of starting with a user ID, turning it into a user, turning it into an email, and then doing something with it. This is very straightforward. It's less straightforward if the intermediate functions can fail. Right? What if the user ID is not valid? Right? And to express that, we can use optional t. So optional t is a type that either holds a t or is empty. And suppose our lookup user function might not succeed. And then it doesn't return the user, it returns an optional user. And then the composition gets a bit more ugly. Because when we look up the user, we don't have the user directly, we have an optional user. So we have to check whether we actually do have a user, and if so, we remove its email. But like fundamentally, we still have a composition. We start with a user ID, we turn that into a user or nothing, and then we logically turn that into an email or nothing. And if you have an email, we do something with it. So can we express that more naturally? Well, the problem is, given an optional user, how do I get an optional email? Well, like this. If I have a user, get me the email, back in an optional, otherwise an empty optional. And this pattern is so incredibly common, there's a member function for that on optional. It's called transform. So optional t has a member function transform, which takes a function, which takes a t and returns a u, and it simply invokes that function on the value if you have one, and then rewrap it back in an optional, and otherwise we forward the empty optional unchanged. And so with transform, we can take our optional user and turn that into an optional email using the email member function. And now we've got our optional email. Now we've got an optional email. And now we also conditionally want to invoke subscriber list at remove. Right? We want to turn the optional email into an action that is potentially executed. And we can use an if statement, but we can also use transform. Right? And it might seem a bit strange at first, but like as you'll see, it's quite natural actually to do it this way. So we have our email, we transform it in some sort of action, and the action removes it from the email list. And this is only invoked if we actually have an email to begin with. It doesn't quite compile because unfortunately we don't have an option of void. So we have to actually return something. In this case, we return monostate, and monostate is kind of like void. It's not just not void, so we can have an optional of a monostate. Putting those all together, this is how our pipeline now looks. We start up with a user ID, turn that into user nothing, transform that into email nothing, and then do our action. And this is a declarative. We don't have any state. We don't have any if. We simply describe our pipeline. User email, do something with the email. And the final, and if at any point, so if the user ID fails, then we will never do the rest of things. Now, what if not every user has an email address? What if the user has an optional email itself as well? Well, then we sort of need to use two ifs because we have two optionals, right? Just calling transform gives us an optional of an email. And if the outer if is true, then we have a user. And if the inner if is true, then that user has an email. And then we need to use the double star. And this is kind of awkward. In general, we don't really want to deal with optional. We sort of want to flatten them out. And just like the join algorithms, we can imagine a join function that takes an optional t and flattens it out into a single optional t. And this sort of throws away a bit of information, but we don't usually care about it. And then we can say join our user, our transform user, and this gives us an optional. Now, of course, it would be a lot better if the transform didn't do the wrapping in the first place. Then we wouldn't need to join it, right? We don't want the extra optional in there. So there's a variant of transform. It's called and then. And then is very similar to transform, but the return type of the function is no longer u, it's optional u. That means that we don't need to wrap it in make optional, right? Because the function itself already returns an optional and can just return the null. And so with and then, we just write user and then the email. And this will either return the email or it's an empty optional, but it's never an optional. So our pipeline now looks like this. We start with the ID, we turn that into user nothing, and then we turn that into email or nothing, and then we've got our action. And we can very easily see which operation can fail and which can't. All the ones with and then can in turn also fail. All the ones with transform can't. Because if the transform one fails, well, then we would just have a nested optional that is then treated as if it were an actual value. Now, what if a user can have multiple email addresses? And then we want to remove them all. In this case, we end up with an optional of a vector of email. And then we've got an if and a for. And this is likewise a bit awkward because what's the difference between a null opt and an optional containing an empty vector? In our context, we don't really care about them. Like semantically, it's the same thing. It means the for loop shouldn't do anything. So to work around this, we have to use cplusplus26 because in cplusplus26, an optional is a range between 0 and nothing. It's a range of 0 or 1s, right? And so we can do our optional transform and end up with an optional vector of emails. And then we can just use the join view to turn an optional range of emails into a range of emails. And if the optional is empty, the join means this is an empty range. Otherwise, it will flatten the nested ranges, and we end up with a single range of emails that we can use with for each to remove. And at this point, we can also just go ahead and use the entire range pipeline. So we have our user, it's either a user or nothing, and then we directly use the transform view because optional is a range. So we use the transform view on the optional to turn it into a range of emails that's either 0 or 1. And then, sorry, it's a range of emails, and then we join. And this pattern of doing a transform and a join is really common. Like we've just seen that with optional before, where we had join and the transform on the optional. And there, the solution was called and then. The proposal for cplusplus29 calls it transform join, because that's kind of what it does. It does a transform and then a join, right? But it just does the same thing. It prevents the nested ranges by flattening it as necessary. There's a question. Optional transform is similar to fmap, and then is similar to the bind operator. Yes, exactly. Now, what if the user ID is always valid? It's just that the lookup, the DB might be unavailable. And if so, we get a DB error, and then we just want to retry it later. And then we still have a pipeline with a composition, but we can't really compose it because composition requires values, right? So we have to turn the exception into values in order to compose them. And for that, we can use expected. Expected either holds a t, which is our value, or an e, which is our error. And so suppose lookup user returns an expected of a user or a DB error. And then we can write code like this. So we look up the user. If we have one, we remove its email from the list. Otherwise, we retry the operation later. And now we've got the pipeline again. We start with a user ID, we have a user or DB error, and then we want to turn that into an email or DB error to turn our action. And I think you know how to do it. You use transform. Expected also as transform. Expected of t function takes a t, returns a u, and we transform the value. And if it's an error, we propagate the error unchanged and don't do anything, just like we propagated null opt in the optional case. And then we can write the code like this. We look up the user, turn that into user ODB error. We transform it, turning it into an email ODB error, and then we execute our action. And the nice thing about expected is that expected of void is a thing, right? So we don't need to do with monostate here. And then after we've done the pipeline, we check for an error. But we can also get rid of this final if by using transform on the error chain. So expected also has a transform error, which leaves the value unchanged, but if it's an error, it invokes the function with the error. And then we can add a transform error at the end. So this is called with the error, but only if you have an error, and then we log it. And then we have to, again, expected doesn't support void in the error case, but this is a good thing. It indicates that we want to explicitly ignore the error at this point by returning monostate. And this is, again, a declarative pipeline. It's a declarative pipeline because there's no temporal relationship between the ones. Like, we don't invoke all of those lambdas at once or in that order, because we will only invoke this one if the first one failed, but then we never invoke these two ones, right? So it's not directly the time dependency, it's just the logical dependency between the function. Now, what if querying the email could also fail? Well, then if we use transform, we end up with an expected of an expected, just like we did with optional. And then just like with optional, we need two ifs because we have two things. And just like with optional, we could write join, which flattens an expected of an expected and returns a single expected, and merging the two errors together. Crucially, this E and this E has to be the same, otherwise we can't merge it. Otherwise we would lose some information. And again, just like with optional, we also have and then, which doesn't do the wrapping because the function is expected, no pun intended, to already return an expected. And so this is how that looks. And then we can write the pipeline like this. So we look up the user, and then we query the email. We do an action on success. We do an action on error. And again, it is really obvious which operation can fail. Only the ones with and then. The ones with transform, they can't fail. And that's how you declaratively process stuff. One downside of this style is that stood expected requires that we've got the same error type, right? So if you first query a value, and then you want to pass the string into an int, and this can either fail with a DB error, and this can fail with a parse error, then like if you want to do both using and then, right? So we query the value, we pass it, and then we print it. Like, what's the return type here? Well, it's a variant of like this error or that error. But unfortunately, and then doesn't compile because it requires that the error is the same and doesn't realize that it can like somehow turn that into a variant. So you have to be awkwardly like cast it first into the appropriate variant, and this is all kind of ugly, right? But this works. We take the result, we cast it to know which error type we want, and then we pass it the value, and then we transform it. Would be a lot nicer if expected was sort of like a pack of E's, and then it either has a T or one of the errors, and then could automatically accumulate. This would be nice. But right now you sort of need like a common error type for everything. So the takeaways here is you can use stood optional and stood expected to model optional and fallible results. If you do that, you have them as values, and then you can compose them really nicely. You can use transform to process new values. You can use transform error to handle errors, and then you can use and then to chain them with another function. And this is a nice thing because at a glance you can see which are the operations that can fail, the ones with and then, and which are the ones that can't, the one with transform. And this is a bit awkward in C++, because you can't really mix different kinds of failure optional this. Like you can't mix a function that returns an expected with a function that returns an optional. You sort of need to decide on one thing. Okay, the fundamental question I'm gonna talk to after on the talk about it after. And if you do this sort of I don't want to add text. If you do this sort of transformation, you minimize if, right? Using transform and then it's declarative. You don't have to bother with if. Now, finally, let's look at composing IO. In a function programming language, all functions are pure. That means that you do not have any side effects during computation, and they will always result in the same value when called with the same input. That means that you do not have global state, and that you can't interact with the outside world at all. Because a function like readInt, which returns an int for standard in, isn't pure. Every time you call it, you get a different value. Now this begs the question, how do you do anything if you can't interact with the outside world? How would you write a simple program like this that reads an integer from standard in, squares it, and writes it out to standard? Well, the idea is you cheat. Instead of directly getting an int, you talk about actions. So the readInt function doesn't return an int, it returns an action that will read an int. And the writeInt function doesn't do anything, it simply returns an action that will write an int. And these are poor functions, because every time you call it, you get the same action back. Because they don't do anything, they simply describe what should be done. Well, I mean, then you still can't write the function, because when you call readInt, you don't have an int, you've got an action that will read an int. So how do you multiply them? Well, you can imagine that we can compose them using transform and end then. So you can imagine that when we call readInt, we get an action that returns an int. And our action type has a transform method, which we can call. So we can call our transform, give it a function, an operation, that is called on the value when that action is executed. And the result will be a composed action that consists of first reading an int, then passing that to the function, and returning the result of that function. And then we can chain it using another action. This is one that takes writes the int. And the result will be an action that will read an int, square it, and write it up. And here we have to use transform for this call because we return an int. But here we have to use and then because our function directly gives us another action. And if we use transform here, we would end up with an action of an action, which is not something we want. So we use and then. And all of this is pure because we haven't done anything so far. We've simply composed actions. And then in our main function, where we actually get the action, we run it, and this is the non-pure thing. Because at this point, we actually start reading an integer, passing it to the lambdas, doing the work, and writing it out. And now in a pure functional programming, essentially all your program does is up here. You don't have the main function. Like all the Haskell program does, it composes actions. And the actual execution of the Haskell program happens after the Haskell program is done, because then we start actually doing the action, we start doing the side effects. And that's sort of how you can cheat and only deal with pure functions by still doing things. Instead of talking with values, you talk with actions. Now, of course, functions in C++ don't need to be pure, right? So this is like academically interesting, but what's the point? Well, it's still a good idea to separate I/O from computation. If you write your code in such a way that you have computation function that takes some input and produces the output without doing any I/O, this makes it much easier to test. This makes it much easier to swap out input or output procedures. And in general, makes it a lot nicer because you've completely decoupled the computation from the I/O. And the sort of action approach can help with that, right? You can write a pure function that talks about computing, like manipulating actions, where the actions are the one that give you the. And even outside of I/O, this general approach of like composing actions in a very declarative way and then execute them later is incredibly useful. And it is, in fact, the entire basis of the new multi-threading library of C++26. So C++26 will have something called standard receivers, which allow us to do multi-programming and asynchronous programming in a very convenient way. So consider this code. This code takes a scheduler. And a scheduler is simply like some handle to a thread pool. So the scheduler, we can schedule work on a scheduler. So when we call execution schedule, this returns something that will then resume on the given scheduler. And we compose them using the pipe symbol, just like with use, and pass it to then. And then is what we call transform in the rest of the talk. So then takes all the values produced by the schedule thing. It's called a sender. So then takes all the values produced by the schedule sender. In this case, it doesn't take any, so it doesn't take any arguments, and does something with them. And in the case here, the thing we want to do is we want to print the 10th Fibonacci. But because the scheduler only continues on the thread pool or something, this means that this work is then executed on the schedule. But crucially, because we're only composing actions at this point, we haven't done anything. We've simply declared, so we've got the action A, which executes using the scheduler. And once it's done, once it's on the scheduler, it will print the 10th Fibonacci. And then we also do a similar thing with a different action. So in this case, we want to check whether 42 is a prime number. And we also schedule that on the schedule. And then what we want to do is we want to say, okay, now I want to do both. So we call when all, give them all our actions. And when all is an action that is only done when all actions that we pass to it are done. So now we've built up our entire pipeline. Now we sort of described the work that we want to do. in a declarative way. And so far, we haven't done anything. And only when we pass them to the sync wait, it means, hey, start executing, and sync wait in this case blocks until this. So at this point, we will start scheduling stuff on the thread pool, do our things, execute both of them in parallel, and we're done. Right? And because we've done it in a very declarative way, this makes it very straightforward to do multi-threading, because you don't have to wrangle any threads or anything. You simply describe the actions that you want to do, compose them in a declarative way, and only execute them at the very end. So by declaratively building plans and executing them later, it allows us to separate I/O from computation. So there was a question about this specific I/O action. I haven't written any I/O action. It's not in the standard library or anything. It's just an example to illustrate how it would be done. How it would be done in Haskell. Right? It's just the general idea. So to answer the question, yes, you would probably have some function to like sequence actions inside actions. And if you do this composition of actions, you minimize impure functions. Because all the actions are pure, you declaratively build your plans, and you execute them. Now to conclude, you might have noticed that my talk was a bit repetitive. Right? So we first looked at ranges. And a range is something that contains 0 or more values. And you've got views like transform, which changes those values. Or views like transform and join, which changes those values using a function that itself returns another range of values. And when you don't want to deal with nested ranges, you can use join. And then we looked at optional and expected. They logically model something that contains a value or nothing, or an error in the case of expected. And then you've got the member function transform, which changes that value, but like still keeping it inside the optional or expected. Then there's a function and then. This changes the value using another function that returns a value or nothing or an error. Right? And just like transform join, this sort of avoids the nestedness. And if you end up with nested things, you can imagine writing a join function that flattens them out, just like you can use the view. And finally, we looked at action. And look, we can also say that the action sort of contains a value in the future. Right? It describes how to get a value, but it's not there yet. But like it contains a value in the future. And when you do the transform, you can change the value. Right? You can compose them and change the value without actually having it, because you simply say that, hey, once you have the value, please change it using this function. Similarly, we have and then, if you want to change the value with something that involves another I/O action. And this prevents the nesting of I/O action inside I/O action. We can also imagine writing a join that flattens a nested I/O action. But crucially, this is kind of different compared to the other ones, because if you've got a range or an optional, you can get the value out of there. If you've got it in an I/O action, you don't really get the value out of there. All you can do is run the action, right? And at this point, you deal with side effects. Because it's a value in the future, right? You can't get it. So all you can do is transform and compose it in various ways, but you can't really get it out of there. But like, if you look at it this way, all of those things are essentially the same thing. They're all like some container of things, and you all can transform them in various ways. And the difference is, and the similarity is because all of those are monads, right? Monads are these sort of like weird things from functional programming, but it's a concept that comes up over and over and over, as we've seen in this talk. And like famously, monads are this really complicated thing that's really hard to explain, but I think it's actually really simple, because in C++ speak, a monad is simply a type that has a transform, that has an and then, and it has a join, right? As we've seen in the talk. And then you also need some way to like build a monad from a value, because otherwise you can't really start with anything. And you don't need all three functions, like you can implement one in terms of the other two, and there's some relationship between them, but like fundamentally, this is what it is. You can think of a monad as some sort of box of some value. And you can transform this value by keeping it inside the box. And monads come up over and over in functional programming, because monads are what enable composition. So to conclude, functional programming is all about composition. And monads come up in functional programming because monads is what enable composition. Using monads, you can chain various functions together in a very natural way. So if you want to do functional program in C++, write your building blocks using efficient, optimized, and well-tested C++ code. And it has to be well tested because this is where you sort of deal with all of the ugly state and all the stuff like that. But then you can compose them using high-level building blocks using functional programming paradigms. And that's how you write functional code in C++. So before I head over to the gather-tone, I will just answer the remaining 2 questions in the chat really quick. So what about or else? Or else is also a function unexpected or optional, and it allows you to get out of the monad. So it's not really a fundamental thing of a fundamental part of the monad, because you can't really write like or else before an IO action, right? Because you can't really get it out. It's still a useful function, but it's not part of the general pattern. And so they answer the fundamental question: what are the use cases in which you think functional programming declarative style can be used, or where such a style can be used? Well, and I think they can be used all the time, anywhere where you identify building blocks and you want to compose them in a very declarative way. This comes most often up with ranges. Like range adapters are a really natural way of composing stuff, but also like when you deal with functions. Like as soon as you like don't have local variables that you modify, you can say that you're writing stuff in a functional programming. It's really not like a big deal, right? Like every time you have a function that has only like const local variables, you can say I'm doing functional programming stuff in some sense, right? So it comes up all the time. And you don't really need to think about it. Just think about the goal. Okay, I want to compose stuff using building blocks that already exist in a very declarative way. And finally, what is monadic lifting? Monadic lifting is a way, so when you take the optional t and you transform it using a function, the optional will invoke the function with the value that it currently contains or nothing. But in some way, you can also see that taking the function that takes a t to a u and sort of turning it into a function that takes an optional t and returns an optional u by simply not doing anything if the result is empty. And then you've got a lifted function that works in the monad directly. And with that, I'm done. I'm going to hop over to gather-tone after this. I thank you very much for listening. I hope you enjoyed the keynote.